Hi, I'm Mark Barsamian. In this video, I'll be talking about slopes of secant lines and tangent lines. It will be one of our more difficult videos involving introducing a lot of new concepts, and the corresponding homework is also one of the more difficult homework sets for the semester. The corresponding reading for this video is from section 2.4 of the book, Rates of Change, and more specifically the beginning of that section, pages 130 to 135, and the first three examples. And the corresponding homework is the one that I mentioned that was one of the harder ones for the semester, homework 25, involving 5 problems. In this video, I'll be introducing a number of important new concepts, but I'm going to do them in the context of working on 2 examples. The first example is an extended example involving this function f of x, this quadratic polynomial, and we'll have many parts to this example. So in part A, the job is to just simply draw the graph. Notice that the function f is given in standard form. We can tell some things about the graph just by looking at the standard form. First of all, it's a second-degree polynomial with a negative leading coefficient, so that means that the graph will be a parabola facing down. The other thing that the standard form tells us is that plus 5 tells us that the graph has a y-intercept at the point 0, 5. That's all from the standard form. Now let's look at the factored form of the function. So the factored form tells us that there are 2 x-intercepts at x equals -5 and x equals 1. So based on that information, just by scrutinizing the standard form and the factored form of the function, we can make a graph fairly simply without having to make a table of x, y values. So that's a very crude graph, but it conveys the important information, the shape of the graph and the key points that we can get just by scrutinizing the form of the function without doing any grungy calculations. All right, question B. For the same function, find these 2 things and use that info to label 2 points on the graph with their x, y coordinates. Well, we will do this by starting with the empty form of the function and then substituting in x values. So notice that at these 2 x coordinates, the y coordinates are both 8. We will use that information to label 2 points on the graph. I'm going to draw a new graph so we can see the progress. So there are the 2 points whose coordinates we now know from our calculations. Question C. For the same function, draw the secant line that passes through the points that have coordinates -3, f of -3, and -1, f of -1, and find its slope. Well, that is going to be just simply the line between those 2 points that we just drew. So I'm going to copy this graph and move it down to the next page. So the line that we need to draw is the line that passes through those 2 points. And we need to find its slope. So we computed the slope using the standard delta y over delta x form, and we got, of course, that the slope is 0, which we were expecting because that's a horizontal line. Now that slope calculation that we just did is related to a more general definition, that of the average rate of change. So it's defined this way. The average rate of change of a function f from x equals a to x equals b means this number that you obtain using this calculation. So in other words, that number is the slope of a secant line that touches the graph at 2 points. So the average rate of change, m, is a number. It's a number that's the slope of a line. So for question D, it's this question. For the same function, find the average rate of change of f from x equals -3 to x equals -3 plus h, where h is not equal to 0. Well, we need to build that red quantity. Remember what that red quantity is. That red quantity is that circled thing. So we simply build that form. Now we can simplify this sum immediately. We see that the -3's in the denominator cancel each other. That cancels that. Now we already have this quantity, f parentheses -3. We computed that on the previous page. But we need to get this quantity, f of -3 plus h. So we'll start with the empty version. So our result is that this quantity, f of -3 plus h, is equal to this expression. So now we need to take the quantities that we have found and we need to build this expression. That is our m. The average rate of change is this quantity m. So there we've substituted in our expressions, and now we can simplify. Notice this 8 cancels that 8. Now it sure looks like we can cancel, but we need to be careful and we need to be clear. To be clear, I want to factor out an h in the numerator. Now it really looks like we can cancel h over h, but we need to be clear why we can do that. What do we know about this h? Notice that we're told that h is not 0. Good thing, because we couldn't even get as far as we did if h was 0. Because if h was 0, this whole expression would have been undefined. So we're told that h is not equal to 0. And there's our result. M is the quantity 2 minus h. Now, we're going to explore this result by filling in this table and drawing the corresponding secant lines on the graph of f. So when h equals 2, what is the slope m? Well, we have to go up and use our formula. M is obtained using that formula. When h equals 1, when h equals 0.5, it's a little bit crowded, so I'm going to put the calculation over on the side. So those are all numbers that are slopes. They can be interpreted as slopes of secant lines. Now, for each of those calculations, what's the x-coordinate of the second point? What do I mean there? Let's go back up. We were supposed to be finding the average rate of change of f from x equals -3 to x equals another nearby x value, -3 plus h. So the first point is the point that has x equals -3, and the second point is the point that has x equals -3 plus h. So now we can find the x-coordinate of the second point. So let's draw those lines on the graph of f. So there are our 4 secant lines. Notice a couple of things about these secant lines. When h gets closer and closer to 0, the second point gets pulled closer and closer to the first point. And the slopes of the secant lines get closer and closer to the number 2. Now remember that the slope numbers are the average rate of change of f over some interval on the x-axis. So when h gets closer and closer to 0, those intervals on the x-axis are getting shorter and shorter. If we take the limit of these slopes as h goes to 0, the result of that limit is called the instantaneous rate of change of f. So let's look at this in symbols. So here's the slope of a secant line. And then parked in front of that slope calculation is a limit expression, which means that you're supposed to imagine what happens to the values of those green slopes when h gets smaller and smaller and smaller, closer and closer to 0. So for question E, for this same function, we're supposed to find the instantaneous rate of change of f at x equals -3. Well, let's go back up again and see what that means. The instantaneous rate of change of f at some number means that we have to compute this. So on that line, I've just simply copied down the definition of instantaneous rate of change of f at x equals -3. So that's what we need to build. Now, we've actually done a lot of this work already. Notice that the thing inside that ratio is a secant line slope, which we calculated in the previous problem. Now let's go up and see what that result was again. That expression, f of -3 plus h minus f of -3 over h, after we simplified, turned out to be just 2 minus h. Okay, now we have a limit. This is a polynomial function with variable h, not x. So we can use our theorem about finding the limits of polynomials. So the result is when we use Theorem 3 that tells us we can just substitute in h equals 0, we get the result that m, this instantaneous rate of change, is the number 2. Notice that as h gets closer and closer to 0, and the second point gets pulled closer and closer to the first point, the secant lines appear to be getting closer and closer to an imaginary dotted line. Let's go back up to the graph and draw in that imaginary dotted line. Now I'm not going to draw it dotted, I'm going to draw it solid so I can erase it more easily. So notice that those secant lines seem to be getting closer and closer to that red line. We call that imaginary line the line tangent to the graph of f at x equals -3. Now, if we had to guess the slope of that line, a reasonable guess would be the number 2, because that's the number that the secant line slopes are approaching. Let's go back up. Look, in this table, the slopes are getting closer and closer to the number 2. And those secant lines are swinging closer and closer towards that imaginary tangent line. So if we had to guess what the slope of that red line would be, a reasonable guess would be it would be the number that these numbers seem to be getting closer and closer to. In other words, these are the slopes of those secant lines, and this is saying imagine the number that those slopes are getting closer and closer to as you pull the second point closer to the first point. Oh, hey, we found that that number, that limit, turned out to be the number 2. That's the number that those secant line slopes seem to be getting closer and closer to. That's how we get to this definition of what's called the tangent line. It's the line that has these two properties. First of all, it contains this point that's called the point of tangency. So on our graph, the line contains that circled point. The other property is that the line has slope that's the number obtained by that calculation of that limit. And that so that's called the tangent line slope, and that's also referred to as the slope of the graph at that x value. Question F. So for our function, f of x equals minus x squared minus 4x plus 5, find the slope of the line tangent to the graph of f at x equals -3. Well, this is just asking us to do what we just did. Now, let's comment a bit about this notation. So we're being asked to find the slope of the line tangent to the graph of f at that x value. We just saw the definition of what that means. The tangent line slope is this computation. Now, there is a symbol that I snuck in here. It's this symbol, f prime parentheses a. What's up with that? That symbol shows up in this definition of instantaneous rate of change of f as well, f prime parentheses a. That symbol is spoken the derivative of f at a. So the derivative of f at a is the same as the instantaneous rate of change of f at a. It's denoted by this symbol. It's obtained by doing this calculation. It's a number. And that symbol f prime parentheses a, stands for a number that is also the slope of the tangent line. So in this question, that's what we're being asked to find. The slope of the tangent line is denoted by these two symbols, and it's obtained by doing this calculation. Well, we just did this. We did this calculation and we got the number 2. Now I want to talk about the equation for the tangent line. Remember that the point-slope form of the equation of a line is useful. If you have a line that has these two properties, contains a known point, whose coordinates are AB, and has a known slope, M. If you have a line that has a known point and a known slope, then it's easy to get the equation of the line. You just build this expression, y minus b equals m times the quantity x minus a. So you just take the x and y coordinates of your known point, and you take the number that's the known slope, and you plug them into this form, and you get a line equation. Now let's think about what we know about the tangent line. The tangent line was defined to have two properties. It is defined to have this point and to have this slope. So if we know those two things about the tangent line, then it's a straightforward thing to construct an equation for the tangent line. We just substitute those known quantities into the point-slope form of a line equation, and we get this thing. That's what we get when we substitute that known information about a tangent line into the point-slope form of the equation of a line. So this is the point-slope form of the equation for the line tangent to the graph of f at x equals a. It's that equation right there. And it comes from knowing this stuff about the tangent line. Question G for our function f of x equals minus x squared minus 4x plus 5. Do this. Find the equation for the line tangent to the graph of f at x equals, that should say, minus 3. Well, let's remind ourselves what we need to build. So that's just the general form of the equation for the tangent line that we discussed on the previous page. Just that thing. That's what we need to build. So what should our strategy be? Well, in order to build this equation, we need to have things ready to populate this form. In other words, we need to have these three things. So our strategy should be get those parts. So what is A? Well, remember in this equation, the letter A is the x-coordinate of the known point. Well, we have a known point. Its x-coordinate is x equals minus 3. That's the x-coordinate of the point of tangency. So our value of A is A equals minus 3. So that's one of those three parts that we need to populate that equation. We also need this thing, f parentheses A. But f parentheses A means f parentheses minus 3. Oh, we did that way back in the beginning of the problem. So f parentheses A is the number 8, and remember that's the y-coordinate of the point of tangency. Okay, now the last thing that we need to get is this thing, f prime parentheses A. But remember that our value of A is A equals minus 3. So that means that f prime parentheses A means f prime parentheses minus 3. Now we did that in an earlier part of the problem. We found the slope of the tangent line. That's what that symbol stands for. So we found the slope of the tangent line was the number 2. All right, so we have got the parts that we need to build the equation. So now let's substitute parts into the equation. And then that's the point-slope form of the equation of the tangent line. We should convert to slope-intercept form. And we convert to slope-intercept form by solving for y. So our result is that the equation for the tangent line in slope-intercept form is this red circled equation. That's the end of example 1. Now I want to talk a little bit about the terminology of position and velocity. So one of the main driving forces behind the development of calculus was the effort to describe the motion of objects, the motion of the planets. We are going to be doing some of that in our course. So we're going to be describing the motion of objects, and when we do that, x is going to be a variable that represents time. And we're going to be talking about objects moving in one dimension. What does that mean? It means that an object can go forward or backwards, or like on a curving railroad track, but basically can't turn. There are no choices that can be made. So in that kind of situation, a single coordinate can keep track of the position. You can say that you have moved 5 miles forward from your original position, or 5 miles backwards, and it just means along that railroad track or along a straight road and so forth. So the position function gives you the value of the coordinate, that's your position coordinate, at a given time. So in our book, the position function is called f. That is, at time x, the coordinate of the object is given by the number f of x that's obtained from that function. So the words average velocity from time a to time b mean the same thing as average rate of change of position from time x equals a to time x equals b. So in other words, the average velocity is obtained by doing this computation. And the words instantaneous velocity at time a mean the same thing as instantaneous rate of change of position at time a. So in other words, you get the instantaneous velocity by doing the computation for the instantaneous rate of change. This computation. So in example 2, we have a cyclist riding a 50-mile bicycle race. And at time 2 hours after the start of the race, the cyclist is at the 40-mile mark. And at that instant, the cyclist is riding with a velocity of 18 miles an hour. So question A, let x denote the time in hours since the start of the race, and let f of x represent the distance traveled in miles at time x. Let's draw a graph that illustrates the given information. So 50-mile bike race, a bike racer might ride 20 to 25 miles an hour at a high speed, and maybe 15 to 20 miles an hour going up hills. So, and you would imagine that the cyclist would slow down as time goes on. So I would imagine the graph starts going up pretty quickly and then sort of doesn't go up as quickly. So there's the given information that the cyclist is at the 40-mile mark 2 hours after the start of the race. Now, how would the graph of the position function look? Well, presumably the cyclist started out maybe at a higher speed and it slowed down a bit. And you can see that at some later time, the cyclist is going to get to the 50-mile mark. Now that's the given information that at 2 hours the cyclist has reached the 40-mile mark. How do we convey the fact that the cyclist at that instant has a velocity of 18 miles per hour? Well, that means that if we look at the slope of this graph, it's going to be 18 miles per hour. Because remember that velocity is the same as instantaneous rate of change, and instantaneous rate of change is the same as slope of the tangent line. So at that instant, the slope of the tangent line is 18. representing the fact that the cyclist has velocity 18 miles per hour. So that's a graph that illustrates the given information. To make the graph, we had to understand the idea of the position function, and we had to understand the idea of velocity as being the slope of a line tangent to the graph of the position function. Question B, find the cyclist's average velocity during the first 2 hours of the race and illustrate your result using the graph. Well, let's go back up and look at our given information. We're told that at time 2 hours into the race, the cyclist is at the 40-mile mark. So in 2 hours, the cyclist has ridden 40 miles. That means their average velocity would be 20 miles per hour. But let's do this the official way, using the average velocity calculation. So there's the official way of setting up the average velocity calculation. Now let's go up and look at our data. F of 0 is 0. At time 0, the position is 0. F of 2 is the number 40, because at time 2 hours after the cyclist has started the race, the position is 40 miles. So the cyclist's average velocity is just what we already knew intuitively, 20 miles per hour. Now the question is, how do we illustrate this result using the graph? The key is to remember that the average velocity from time x equals 0 to time x equals 2 is defined to be the number m that's also the number that's the slope of the secant line that touches the graph at time x equals 0 and time x equals 2. So what we need to do is grab our graph from before and draw in that secant line and label it. Well, I've copied the graph from before and I've put it on the next page. So let's go to that graph, draw in that secant line and label it. There's the graph from before. We're going to draw the secant line that touches the graph at x equals 0 and x equals 2. That's this green line. And we should explain what it has to do with the problem. So there you can see that the average velocity over the first 2 hours is 20 miles per hour. At time t equals 2 hours, the cyclist's instantaneous speed is 18 miles per hour. So the cyclist is slowing down a bit as we come towards the end of the race. Okay, let's go on to the next part of the problem. Question C, find the equation of the line tangent to the graph of the function at x equals 2. Well, the solution to this relies on the idea that the instantaneous velocity is the slope of the tangent line at that time. Let's go up and look at our graph again. There's the tangent line, and we knew that tangent line had to pass through that point, and we knew that the slope of the tangent line was 18 because we were told that that's what the cyclist's velocity was at the instant where time was 2. So for that tangent line, we know 2 bits of information. We know the tangent line passes through that point, and we know the tangent line has that slope. So the 2 things we know about the tangent line are that it contains that one point and it has that known slope. So we can substitute those things into the point slope form of the equation of the tangent line. Now that we've substituted in, we should convert this to the more common slope-intercept form. We do that by solving for y. So there's our equation for the tangent line. That's the end of this example. The last thing I want to do is discuss your homework 25. That homework has 5 problems. As I mentioned at the start of this video, this is one of the harder videos of the semester, and homework 25 is one of your harder homeworks of the semester. Now, homework 25 has calculations very similar to the calculations that I did in this video in example 1 and example 2. So I'm going to discuss those 5 homework problems and how they relate to the calculations in the examples. In homework problem 1, which is similar to book problem 2.4 number 9, part A, you're asked to compute the value of a difference quotient. Well, a very similar calculation was done in example 1C. In part B of problem 1, you're asked to compute a difference quotient involving the letter H. Well, we did one of those in example 1D. And in question 1C on the homework, you're asked to compute the limit of one of those expressions. Well, we did that in example 1E above. In homework 25, problem 2, in part A, you're asked to compute the slope of a secant line through 2 points, a comma f of a and a plus h comma f of a plus h. Well, that's going to involve computing the value of a difference quotient, one of these things again, which is just like what we did in example 1D above. Now in question B, you're asked to find the slope of a graph. Now remember that the slope of a graph is the same as the slope of the tangent line, and that's denoted by this symbol, and it's obtained by doing this calculation. That calculation is what we did in example 1E. In part 1C, you're asked to find the equation of a tangent line. Now remember that the strategy was we want to build this equation. And the strategy that I used in example 1G was I first got the parts, so identified the value of A, I found the value of f of A, and identified the value of f prime parentheses A. In that example, all of those values had been computed earlier in earlier parts of the example. If you're in a problem where you have not already computed those things, then you'll have to compute them at the time where you need them. So then once we got the parts, we substituted them into this form of an equation, and then we solved the equation for y in order to get an equation of this form, slope-intercept form. In problem number 3, you're asked 3 questions about a bicycle racer. Well, that's just like that example 2 that we did above. In problem 4, you're asked to compute the slope of a secant line between points a f of a and b f of b, where a and b are some particular numbers. That means doing one of these calculations, like we did in example 1C. In question 4, part B, you're asked to find the slope of a secant line through a point of this form, a comma f of a, and a point this form, a plus h comma f of a plus h, where h is some non-zero number. Well, that means you're going to be led to doing a calculation like that, which is just like what we did in example 1D. In problem 4, part C, you're asked to compute the slope of a graph. Now remember, that means the same thing as the slope of a tangent line, so what you're going to be looking for is denoted this way, m equals f prime parentheses a. You do that by computing this limit, which is like what we did in example 1E. And finally, In part D, you're asked to find the equation of the line tangent to a graph. And that's just like what we did in example 1G above. And then finally, in problem 5, you have a problem about velocity. You're asked to find average velocity for x changing from A to B. Well, that means the same as average rate of change. Remember, I discussed that earlier when I talked about velocity. In other words, you're being asked to compute one of these kinds of things, which is like what we did in example 1C. In part B of problem 5 on the homework, you're asked to find an average velocity for x changing from A to A plus h. So that means you're going to be computing one of these sorts of things, like we did in question example 1D. Finally, in part C of question 5 on the homework, you're asked to compute the instantaneous velocity at x equals a. That means the same thing as instantaneous rate of change. That means you're being asked to find this quantity, which you do by finding this limit, which is what we did in example 1E above. So as long and difficult as this video was, I hope that the examples that we discussed in the video will be useful for you when you do homework 25. That's the end of the video. Thank you.